So let's continue. So the next thing we're going to talk about is what we call electric. So first, I'm going to talk about electric potential energy, which is something that you are familiar with, not in this context, but in the context of mechanics that you did in the first semester. So let's review a little bit about that thing. So what I'm talking about here is if you have some object near the surface of the earth, you know that any object will just fall down due to gravity, and then the gravitational force can be written to be mg. Maybe you don't need a vector sign there because you know it's going to point down. And the reason why every time you drop something it moves down is because the force from the earth is pulling the object down. That's one way of explaining. The other way of explaining is to talk about not electric, sorry, talk about the potential energy. And the way we do it is like this. First, you need to say what is your reference point. And usually the ground is where you call EP, which unfortunately we use EP before the break to be the electric field at point P, but this is different. This is the potential energy. Okay, so P stands for potential and E is the energy. So we choose the ground to be potential energy equal to 0 like this. And then at a height h above the ground, this object will have EP equal to mgh. Right. So hopefully you remember this from first semester. You use conservation of energy to calculate the speed of something, and then you say, okay, potential energy plus kinetic energy is the total energy, and that thing is conserved. Something like that. Okay, so potential energy is mgh. Right, so h is the height above the ground, which we define the potential energy to be 0. You can choose the potential energy to be 0 at different points. It's totally up to you. Okay, you can even say, okay, the potential energy here is 0. Then potential energy of the ground, which is below, then it's going to be negative mgh. That's also fine. Nothing's wrong with that, because most of the time we will be looking at the change in the potential energy, not the absolute value of the energy, of the potential energy. Right. But in any case, I will choose it like this. So a different way of explaining why the object falls down is because by falling down, the object reduces its potential energy, and that's what nature likes to do. Okay, nature likes to put the system at a lower potential energy if it can. And in this case, it can do that. And it does that by going down, reducing h, because mgh is lower when h is lower, right? So potential energy will reduce when you move down. So that's how it works. It's explained exactly the same thing, which is an object falling down, but one is to explain in terms of force, the gravitational force pulling it down. The other one is to explain this by the tendency of potential energy to be lower if it can. Okay, so it's kind of like two sides of the same coin. Right? They are related to each other. So how are they related? Well, I'm not sure if you remember, or maybe one of you has an instructor in physics 1 who did some kind of derivation. I don't know, but usually the way to find the potential energy EP is by integrating the force. Okay, so this is how it's written. So think of this as something similar to work. Remember, work is force times distance or force dot displacement vector. That's work. And potential energy is defined in a similar way, EP. And since usually force is not a constant, it's not a constant force, so you need to integrate it. Right. So you can take this as a definition. Okay. Don't worry about remembering this or how to use this because this is just for derivation. It's not the most important thing here. Okay, so don't worry too much if you don't know what's going on here. So the potential energy is the integral of force times distance. And you have to put in the limit of integration. Usually the limit of integration is from the position that you want, which is any position A, to the reference point. That's how it works. So let's apply this to the situation above, okay? And the situation above is, what is the force? Is the mg force here. And where you are, A, any point A, is from the height h. So integral from h, y equal to h, to the reference point. The reference point is the point where you choose the potential energy to be 0. And that's on the ground. So that's h equal to 0. So integral from y equal to h to y equal to 0. And then what is force? It's mg. And dx becomes dy because we use y as the variable in the vertical direction for the distance. Right. And by evaluating this, then you get mgh. Okay, so that's the potential energy. So we're going to do kind of the same thing. With electric force. So for the electric force, we're going to replace the force that we have here, mg, by the electric force, which is the Coulomb force. All right, that's the only difference. So what are we talking about here? Well, we are talking about the potential energy from the electric force. So imagine that we have one charge, which is again plus big Q, and we have a small charge, which is Q here, and they are distance r away from each other. Right. So we want to see, let's say this one is fixed, meaning that it doesn't move. Right. And this one is what we are free to move around. So we want to see that if we want to move the charge, small q, from a very far away place, let's say here, and even further, as far as you can, and move that to this point, how much potential energy you're going to gain? So it's the same concept as what we had up here, right? That means we're going to do the same calculation. So we're going to write instead of EP, we're going to write U. And this is kind of more like a naming convention, so don't ask me why I use U instead of E, but it's just, I'm just used to this more than the other variable. So U is the potential energy, so maybe I should write it more explicitly. So potential energy, U, which will be as a function of R, is given by the integral of this position R to the reference position, which in this case, we're going to take it to be as far away as we can, which is R equal to infinity. So this is the reference point. So remember what's the reference point? The reference point is the point where we say the potential energy is 0. So in this case, the potential energy is 0 when the two charges, big Q and small q, are infinitely far away from each other. So the influence of the charge of one charge is very small on the other one when they are very far away from each other. So that's what we choose as a reference. And we need to integrate the force, right? So the force between them is just the Coulomb force. So that's going to be K times Q and Q divided by R squared times dr. Right. So this is the force. This is the distance, right? So it's exactly the same formula that we had up there, except I should write displacement. Except it's in the R direction. Okay, so it's the same as this. This is the same. Okay. So let's just perform this integral. Well, K, Q, Q are all constant. So I can take that out of the integral sign. So that's going to be UR, which is the potential energy, equal to K, small q, big Q, integral of R, 1 over R squared dr, from any point R to R equal to infinity, like this. And this one is not too difficult to calculate. And I hope you can do this. But if you don't, then don't worry. Integral of 1 over R squared, you get minus 1 over R. And the limit of integration is from R to infinity, like this. So when you substitute in the limit of integration, you have minus 1 over infinity minus minus, so double minus sign, minus minus 1 over R, it becomes plus. So in the end, you have KQQ divided by R, because 1 over infinity is 0. Right? So this is a simple integral to give us a very important result, which is for a pair of charge, Q and then Q, which has a distance R away from each other, the potential energy is U as a function of R equal to K, Q, and Q divided by R. This is the main result of this part of the lecture. Okay, so the potential energy between a pair of charge, and this is important. Potential energy is always between a pair. Similar to Coulomb's force, is always between a pair. Okay, if you have just one charge, Coulomb force doesn't make sense. Potential energy also doesn't make sense. Okay, so for the force to make sense, you have to introduce electric field. Then you can talk about one charge. Similar here. If you want to talk about potential energy, you need a pair of charge. Okay, one charge, one single charge, it doesn't make sense to talk about potential energy. In order to do that, we need to define another thing, which we're going to do that later. But at this point, let's not do that yet. Okay, so we have the potential energy given by this formula, KQQ divided by R. And you're going to have the sign of the potential energy to be exactly what you have here. So what do I mean by that? What I mean is this. Let's say you have plus Q here, and also plus small q here, and they are a distance r away. This situation, this pair has a potential energy U equal to KQQ divided by R. But if you have one of the charge to be negative, let's say big Q is negative big Q, and small q is still positive q. Now the potential energy, you have to put in negative for big Q, so you're going to have minus QQ divided by R. And if you have negative Q and negative small q, the negative sign will cancel out, so you're going to go back to KQQ divided by R. So the sign matter here. And the other thing is U, which is potential energy. This is strictly scalar. So you don't need to worry about direction or anything like that because it's an energy. Energy doesn't have a direction. So in a sense, it's a lot easier to deal with compared to the Coulomb force, which is strictly a vector. This is a scalar, so you don't need to worry about direction at all. But you need to care about the sign of the charges. If you have positive and positive, potential energy is positive. If you have negative and negative, potential energy is also positive because Q times Q, you cancel out the negative sign. But if you have one of them negative, the other one positive, then potential energy is negative. And actually, it's very important that we have this kind of sign, because remember that the system will try to lower the potential energy if it can. And think about this. So the first situation, we have positive and positive sign. So potential energy is positive KQQ divided by R. What can the system do to lower this potential energy? Because that's what nature wants to do, right? That's what the system wants to do, is to lower the potential energy. So think about this, like how can it lower the potential energy? It can lower the potential energy by increasing R. By increasing R, you increase the denominator, so the value for U is lower. So increase R to lower U. And that makes sense, right? Increasing R means these two charges want to go away from each other. And that's what we expect, right? Because Coulomb force will point them apart from each other because they are repelling. They have the same sign. So this makes sense. And that's also true for the situation down here, where you have the same negative sign for two charges. So the way to lower the potential energy is for the two charges to be further away from each other, because potential energy is positive. Now looking at this, is the other way around, right? It has a negative sign here. So looking at this, how can you go lower? Going lower means going more negative, right? Because negative, let's say negative 3, how do you go lower? You need to go to negative 4 or negative 5. So you need to go to negative larger number. And you can do that by decreasing R. So it's the opposite case. So in this one, you decrease R to lower U. And that makes sense because these are two opposite charges. They're gonna attract each other. So it's natural to expect them to have R, which is closer and closer. And because by doing so, you go to more and more negative of the potential energy. So it's all consistent, right? Potential energy is always going to be trying to go lower, right? And depending on the sign of the charges, it will do that by increasing R, repelling each other, or decreasing R, or attracting each other. Okay, so this all makes sense. Now, what about a system where we have more than one pair of charge? Well, in that case, you just have to write down the potential energy, each pair separately, and just add them up. For example, one configuration that we talked about last time or last week is charges at the corner of a square. Okay, let's just make it easier by just doing 3 instead of 4. So let's say we have plus Q1 minus Q2 and then plus Q3. Sorry, plus Q3. And I don't know what Q1, Q2, and Q3 are in terms of value, but I know the sign. Right? Q1 is positive, Q2 is negative, Q3 is positive. Now, what is the total potential energy of the system? So in order to calculate this, you just need to write down the possible pair of this system. So this is R. Let's just call this A, the distance. This is also A. And of course, then this Q2 and Q3 will be square root of 2 times A apart. Like this. Okay. So what's the total potential energy of the system? So U total will be the summation of U from each pair. So that means it's going to be U from the pair 1, 2 plus the potential energy from the pair 2, 3 and potential energy of the pair 3, 1. And you don't need pair 1, 2, 1 because 1, 2 and 2, 1 is the same thing, right? So be careful not to double count the potential energy. You only need one term for each pair. All right. So what is the potential energy for each pair? Well, for U1, 2 is Q1 and Q2, Q1 and Q2, right? So that's going to be K times Q1 and Q2, but one of the Q is negative, so I need negative K divided by the distance between the charge. Another important thing, and some of you will forget sometimes, is that for potential energy, it's not 1 over R squared, it's 1 over R, okay? So it's just A, not A squared. We are not calculating the electric field here, we are calculating the potential energy. So fortunately or unfortunately, the formula looks almost the same, but they are not, okay? And be careful, be very careful about this. So in this case, 1 over A. So that's the first pair, 1, 2. 2, 3 is this pair. The potential energy is also negative because Q2 is negative, Q3 is positive. So you're going to have negative K, Q3, and then Q2. But now the distance is a little bit further away, so you need square root of 2 times A. So if I color code this, this is U1, 2, this is U2, 3. And then the last one, of course, is 1, 3. Now 1, 3, Q1 and Q3 has the same sign, so you're going to have positive K, Q1, and then Q3. Divide by the distance between them, which is A. And that's going to be the last term. Right. So you just add them up like this, which is very, very convenient because it's all scalar, so you can just add them up. Now if you have the fourth charge, Q4, maybe here, right? So on top of these terms, you're going to have all possible way to pair up with Q4. So you're going to have U34, U14, U24. So you're going to have 3 more terms. Right? So you can see that the more charges you have, the more terms that you need to add up. But in principle, it's kind of the same way that you did here. Okay? So you can calculate the total potential energy, electric potential energy of the system using the calculation that we just did here. All right. So going back a little bit here. So I mentioned that in order for you to say what the potential energy is, you need a pair of charge. Same way as Coulomb force. In order to say what the force is, you need a pair of charge. Just one charge doesn't matter. But sometimes we want to deal with just a single charge. And previously we did that by introducing electric field, right? So we can say what's the electric field from a single charge. We want to do the same thing with electric potential energy. And this will be another source of confusion for you. So the next thing we're going to talk about is called electric potential. Okay, did I just say the same thing? No, because U is potential energy. Here we're going to call V. This is called electric potential. It doesn't have the word energy here, so it's not an energy. Okay, so it's just electric potential. And sometimes we just call it potential, V. And the way we define it is U equal to Q times V. So what's the idea behind this? Well, remember that if we have plus Q and then small q here, the potential energy is U equal to KQQ divided by R, and R is the distance between the charges. So similar to the way we kind of motivate the idea of electric field, we want to say that this small q is interacting with something here, which is produced by big Q. So in terms of the force, it's F equal to electric field times the charge, right? So in this case, we're going to kind of doing the same thing. We're going to say that this charge Q creates electric potential here, but I will just write potential. Create potential here. And then when you put in the second charge, small q here, that second charge, small q, interact with this potential here and give back the same potential energy. So in other words, let's say it creates the potential here equal to V, which is also as a function of R. Okay, so once you put the charge Q here, then the potential energy can be calculated by Q times the potential at that point. Again, I will write things to remind you that this is very similar to force equal to Q times electric field, right? Remember the reason why we have to introduce this is the electric field is created by a single charge, and then the second charge interact with that electric field that gives you the Coulomb force, right? Here's the same thing. So the Q here, big Q here creates a potential. Okay, not yet the potential energy, just the potential at this location. Then this Q, which is the second charge that you bring to the system, interacts with this potential and give the potential energy U, which has to equal to the potential energy that we calculated earlier. So this must be equal to KQQ divided by R. And that's possible if we have the potential V equal to KQ divided by R. Another important result here. And again, I want to emphasize that potential V makes no reference to the small charge, small q, right? Because it doesn't care if small q is there or not. Right? You just want to create potential at the point that you're interested in. Okay, similar to electric field, remember, is equal to KQ divided by R squared. So note the difference here. One is 1 over R, the other one is 1 over R squared. So before we go any further, let me comment a little bit about the unit here. So U is the electric potential energy. So that means U has the unit of joules, as usual, okay, because energy is joules. But potential V, looking at this equation, is joules per coulomb, right? So V has the unit of joules per coulomb, or J per C, or we call this volt, or V. It should be familiar to all of you, right? Because when you go buy a battery, you need to usually specify the voltage. How many volt the battery you want to buy, 12 volt, 1.5 volt. That's the same unit as the potential. Okay, so joules per coulomb gives you volt. And because this is joules per coulomb, which is electric potential energy per unit of charge, it's also a scalar. It's not a vector, unlike electric field. Potential is a scalar. So that means you can just add the potential from how many charges that you have. And even better, you don't need to worry about the direction in this case. Okay. For example, if you have a charge plus Q1 here, and another charge plus Q2 here, and you're interested in the potential V at this point, how do you calculate this? Well, you just see how far away from Q1, that might be R1, how far away from Q2, that might be R2, and V is just V from 1 plus V from Q2. And that's going to be just KQ1 divided by R1 plus KQ2 divided by R2. You just add them because they are scalar. You don't need to worry about the direction, right? So a very different question is, what is the electric field at this point? In that case, you need to draw electric field here, and then you need to add them like you add vector. So it's a little bit more complicated, right? So dealing with potential is a lot easier because you don't need to worry about the direction. And if one of the charge is negative, let's say this is negative Q2. Well, you just put in negative for that potential, and that's it. That's the only thing that you do. Okay, so you can see how easy it is to calculate potential at any point. You just add them up. Okay, so if you have multiple charges and you want to see the potential at particular point, you just add them like this. So, okay, we know the potential at this point. So what's the deal? Like, how can we use this information? Well, in the case where you put in the third charge, which is small q here, right? You want to see what is the potential energy of this guy. Then you just use U equal to Q times the potential that you just calculate up here. Right. So that means you don't need to recalculate stuff when you change this small q to different value because you already know the potential. It's always going to be potential energy times potential times charge equal to potential energy. Right. So this value, what does it mean physically? Is so U equal to Q times V here. This one is equal to the amount of energy required to move small q from infinity to this point. That's what it means for you. Okay, so it's the amount of energy required to move small q from infinity to this point, right? So imagine this situation where this is positive, then this is positive, and small q is also positive, right? So let's say these two are fixed, so they don't move. Okay, so this is positive, and everything is positive, so they want to repel each other, right? So if you want to move plus q from really far away, you have to fight against the repelling force from Q1 and Q2 in order to reach this point. Right. So the potential energy is positive. Because if you let go of your hand here, then this charge will just fly out to infinity, which has zero potential energy. So that's what it means here. But instead of calculating the potential energy the way we did, you can calculate the potential first, and then calculate the energy by multiplying Q to the potential like this. Okay, so I think that's it for this session. It's two very important concepts, and it can be quite confusing. So take your time to look through this again, and let me know if you have questions, maybe in the next lecture on Monday or any later time. Okay, but for today, that's it, and thanks for joining, and I'll see you on Monday then. Okay, so take care everyone, and have a good weekend.